you were watching, it's like the first 15 minutes or 30 minutes, you're not gonna get other work.
All right. Hi, everybody. We have been talking about these probability distributions here in 12.1. And hopefully you noticed that, like, some of these probability distributions are kind of like a hassle to come up with, right? To build out, to calculate all the individual probabilities. What we're going to do in the next two sections is we're going to look for situations where, depending on the circumstances, the way we calculate the probability, the individual probabilities would remain the same. Kind of cook up a formula to make this probability distribution process a little bit simpler, rather than having to like build these tree diagrams and stuff every time, which are kind of a hassle. Everybody okay with the plan? So that's kind of framing what we're about to do. So this specific structure, probability structure we're going to talk about today is the binomial distribution. Okay, so it's a type of probability distribution obtained by listing the outcomes of a binomial experiment. So the binomial experiment will be like, depending on how your random variable is stated, you might say, aha, that situation's a binomial experiment. So this probability distribution created from this random variable will just be a probability distribution. I can use these formulas to kind of calculate the probabilities rather than having to do this by hand. Is everybody okay with the idea? So I use this word binomial experiment, and you're probably like, well, gee whiz, Mr. Kulek, a binomial distribution as a result of binomial experiment, like, that didn't really tell me much of anything. What the heck's a binomial experiment mean? Well, a binomial experiment is a situation that contains the following four properties. So there's a known number of trials performed. We abbreviate that number of trials with the lowercase letter n. Each trial has only two true outcomes, success or failure. Okay? So the bi in binomial, the prefix bi means two for the two outcomes, success or failure. So for example, if our random variable is the number of heads we get when flipping a coin 5 times, what would count as that is a binomial experiment. What would count as the success in there?
Getting heads.
Getting heads. And the number of trials would be 5, because we flipped the coin 5 times, we said. Everybody's okay? Okay. The probability of success is constant from trial to trial. So is that true for flipping a coin? Does the probability that heads comes up change in between flips? Should not, right? Everybody feel good still? What's a situation where that probability could change in between trials? If you're selecting things from a set without replacement. So like drawing cards from a deck of cards, if you're not putting the card back, the probability the next card is drawn is out of 51 instead of 52. The probability has changed. For drawing names out of a hat, if you don't put the name back in after you've drawn it, probability has changed. So you need to have a replacement for this, for your situation to possibly be binomial if you're like picking things from a set. Is everybody okay? And the last is that all the trials are independent. So the independent guarantees that the probability doesn't change in between trials, right? Okay. So what we're saying here now is, or what I'm promising you by the end of today's lesson, if we know the number of trials and the probability of success, we can then calculate the probability of any outcome for our binomial distribution with a formula, rather than having to like build out a tree diagram and count the number of ways something happens and calculate the probability of each way that the thing can happen and add stuff up and be nice and clean and easy. That's my promise by the end. Cool? Okay. Worth noting that because there's only two ways something can happen, either success or failure, if the probability of success is P, the probability of failure then has to be 1 minus P. In some textbooks, you will abbreviate that with the letter Q, just to like tighten the formula up a little bit. But just keep in mind when we talk about Q, that's the probability of failure, that's just 1 minus P. Pretty good? Okay. And notationally, the way that we say that a probability is a binomial distribution, or a random variable is represented by a binomial distribution, is we write the name of our random variable, in this case the x, and we do that little squiggle, and we write the capital letter B for binomial, and we write the number of trials and the probability of success, because those are the two things that uniquely define the different types of binomial distributions. Right? If I flip a coin 10 times, a fair coin 10 times, that's a different binomial distribution than if I flip the same fair coin 3 times. Right? Like, there's different binomial distributions. The probability of successes will be different. Fine, but the formula to calculate them, same. Cool? All right. So what we're going to do is we're going to kind of walk through an example that's going to help us discover what this formula is going to be that we'll use to calculate these binomial probabilities. So far, so good? All right. So here we say determine the probability of getting exactly 2 heads in 3 tosses of a biased coin, where the probability of heads is 2/3. So you have like a weighted coin that comes up heads 2/3 of the time, and want to calculate the probability of getting exactly 2 heads in 3 tosses. So the way we would have done this prior to the end of today is we would have built like a tree diagram to do this, right? So one branching for our first toss could come up as heads or tails. The probability of getting heads, we're told, is 2/3, and that means the tails is 1/3. And then I'll draw 2 more sets of branchings for the second toss, and then 8 more sets of branchings for the third toss. And I've kind of consolidated that all there. Does everybody feel okay? This looks familiar on something we have done in the previous lesson. So to figure out the probability of getting exactly 2 heads, I need to look at all 8 of these outcomes and see which ones give us exactly 2 heads. I see 3 of them, right? Heads, heads, tails, heads, tails, heads, and tails, head, head. So I would calculate those 3 probabilities and then add them up. Everybody's okay? So again, exactly 2 heads could come heads, heads, tails, or heads, tails, heads, or tails, heads, heads. What does or tell us when we talk about probabilities?
Multiplication.
Adding. Now to calculate the probability of heads, heads, tails, I need to get heads and tails. I'm going to march down that that first branch. Everybody okay? When I say the word and in probability land, and means multiply. So I do 2/3 times 2/3 times 1/3, or I get 2/3 squared times 1/3, or 4/27. Everybody's okay? If I do the same calculation then for heads, tails, heads, I get the same 2 squared times 1/3, right? And if I do the same calculation for tails, heads, heads, I get the same 2 squared times 1/3. Everybody's okay? So to calculate exactly 2 heads, then I'm just gonna take the number of times the number of different ways I can get 2 heads by the probability, any one of these 3 probabilities, because since they're all the same thing, so the probability of one instance of getting 2 heads, and I have my answer, right? So here I would have 3 times, because there's 3 different ways I can get 2 heads, 2 squared times 1/3, which comes out to be 4/9. Does everybody feel okay in what we've done? So this is our outline for how we're going to build our formula to calculate probabilities inside of a probability distribution. So how many successes do we have in exactly 2 heads? 2, as heads comes up twice. How many failures do I have? 1. And how many different ways can I get 2 heads? 3. So my formula is going to work out to be like the number of ways the outcome can occur times the probability of success to the power of number of successes times the probability of failure to the power of number of failures. Does everybody feel okay with kind of what we've outlined here? And regardless of how we've built this binomial circumstances, like how many trials we do, or what the different probability of success or failure is, this process would not change, right? Because with the situation described, we'd always be drawing a tree diagram. Our tree diagram would always look ostensibly the same. So that's the idea. So here's, again, what we just pointed out is that the 3 different ways we could have gotten 2 heads all have the same probability. That'll be the same for all binomial distributions. So all we need to do is calculate one of those probabilities and figure out the number of ways it occurs, and then we're going to be good to go. Cool.
So would you have to always do the tree diagram before?
No, we're just doing this to like explore how to get to the formula, and once we get to the formula, we're going to streamline this to where you can do it all inside of your calculator and not have to write anything down and draw any more pictures, provided that the random variable behaves as a binomial distribution. Everybody's okay? All right. So again, the tree diagram was fine in that example, but what if instead of tossing the coin 3 times, we tossed it 5 times, or 6 times, or 30 times, drawing 2 to the 30th branchings, like you need a sheet of paper as long as the hallway to like get that thing to expand out. That's going to be a massive, massive tree. Nobody in their right mind wants to do that by hand, right? So let's take an example here. Let's say we want exactly 2 heads, but let's extend this out to 6 tosses and just kind of get a feel for what's going on here, right? Okay, even 6 tosses is going to have 64 branches at the very end. Woof, no thank you, that's massive. I don't want to draw that. I don't want to try to get that on my piece of paper, keep it straight. Yuckarooskies. I would much rather kind of build a formula from that. Again, we're going to note that, okay, is this a binomial distribution? Is there a fixed number of trials? Yes, how many trials are there? 6. Is the probability constant across all trials?
Yeah.
Yes. What is the probability of success? 2/3, right? Because it told us this is that weird coin, the cheater coin. Is there 2 true outcomes, success or failure? Yes, because the 2 outcomes are
It's either heads or not.
heads or tails, right? And heads is our success and tails is our failure. Are these are the trials independent?
Yeah.
Yes, because flipping a coin, that outcome doesn't affect the next coin flip's outcome, right? So we do have a binomial distribution. Because we know all of these things. So what I want is now to use that structure that we've identified to try to streamline solving this and build out like a formula, right? We're still kind of dancing around this. So I'd start by symbolically noting that this random variable that represents the number of heads when we flip this unfair coin 6 times, represented by the random variable x, is binomial 6 2/3. And no matter the order in which I get heads and tails, the probability of one outcome where I get 2 heads is going to be the same. So for the sake of argument, let's just use the heads, heads, tails, 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 tails outcome as our exemplar. And let's calculate the probability of this one way of getting 2 heads. So heads and heads and tails and tails and tails and tails should be 2/3 squared times 1/3 to the 4th. So again, it's the probability of success to the power of number of successes times the probability of failure to the power of number of failures. Right, feel good? And now all we need to do is figure out how many different ways I can get 2 heads when I toss a coin 6 times and multiply by that probability, and I'm going to be at my answer, right? Yes?
So you can use any way of it can be tails, heads, tails, tails, heads, or whatever. It's just.
It'll come out to be that same 2/3 squared times 1/3 to the 4th.
Oh yeah.
Because multiplication is commutative, so it's the same 4 numbers multiplied together, you're going to be good, right? Okay? All right, so we have this. So what we're looking for is the number of combinations. So do you guys remember combination, this term from a previous math class, other than the people that were in AP statistics already? Okay, so a combination describes a situation where the order does not matter. Meaning that, that the outcome heads, heads, tails, tails, tails is no different than tails, 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 heads, heads, right? Like if you roll a pair of dice and you're looking for getting a 7, doesn't matter if you roll 1 and 6 or 4 and 3, it's still a 7, right? Or if you're voting people into student council, it doesn't matter if you elected Bob, Alice, and Jim, or if you elected Jim, Alice, and Bob. The order of the council doesn't matter because there's no assigned positions yet, right? So these are situations where you're talking about like a combination. So you know those locks that you put on your locker? What do you call those? Combination locks. Does the order that you enter the numbers matter?
Yes.
Yes, they're not combination locks. Using the mathematical definition of combination, they are actually permutation locks. A permutation is a situation where the order matters. Is everybody okay? Yes. All right. So the formula to calculate the number of combinations So the notation that you will commonly use is NCR. This is the notation that your calculator uses. Some textbooks use the N as a superscript, and then a C, and then the R as a subscript. Most commonly in a textbook, you write with a parenthesis, N on top, R on bottom, close parenthesis. Notice it kind of looks like a fraction, but there's no fraction bar in the middle. So those are all three different ways you can write. What I'm doing is looking for a combination. But to actually do the calculation, the number of combinations is going to be n factorial divided by r factorial times n minus r factorial. So remember that exclamation point after a number means factorial, right? So like, for example, 4 factorial means 4 times 3 times 2 times 1. Worth noting that because what we're doing is we're talking about the number of ways to count something, or the number of ways you can order something or arrange something. 1 factorial is 1. Most students are okay. If I take one object, how many different ways can I arrange that one object? One way. If I take 0 objects, how many different ways can I arrange those 0 objects? Still one way, right? There's just nothing there. That's still one arrangement. That's why 0 factorial is still 1. That's the one that kind of breaks the multiplication definition. But you have to think about it as arranging things. You know, if you have no stuff to arrange, how many different arrangements do you have? Well, you still have one arrangement. It's the arrangement where there's no stuff there. So everybody, so far so good. Okay. It's also worth noting that how you define success and failure doesn't really matter when it comes to counting combinations. So whether you want to talk about, okay, I have 6 things, and I need to choose exactly 2 heads out of this, and count the number of ways that can happen, that'll be the exact same number as if I take 6 things and I need exactly 4 tails in each thing. So 6 choose 2, we're picking exactly the number of things with exactly 2 heads in it, will be the same as 6 choose 4, the number of things with exactly 2 tails in them, or 4 tails in them. Because if there's 6 total things, if I have 2 heads exactly, the other 4 things have to be tails. If I have 4 tails exactly, the other 2 things have to be heads. Those 2 combinations should be the same, and they are. Does that feel okay? It usually doesn't come on. It's not really a big deal. Okay, so returning to this problem, where we want the number of ways we can get exactly 2 heads when we toss an unfair coin 6 times. Well, that's just going to be 6 choose 2. So we have 6 coin tosses, right? 6 outcomes from tossing the coin. We need exactly 2 of those to be heads. It doesn't matter the order that they come up, whether it's heads, heads, and then 4 tails, or heads, tails, heads, 3 tails, whatever. Doesn't matter the order on that. We're just counting the number of ways it can happen. So I'm going to plug that into my combination formula. So I have 6 factorial divided by 2 factorial times 6 minus 2 factorial. That's where the 4 is coming from. 1 second, Colby, I'll be right with you. I expand my factorials. I notice that, hey, look, there's some stuff that can reduce. I'm left with 6 times 5 over 2, so 30 over 2, or 15. And then I can just multiply everything through, and there's my probability. Colby, what's up?
How do you know when to make the number factorial? Like, how do you know to make the 6 and 2 and 4?
So if I go back to the previous page, see that formula in the middle there? that n choose r is equal to n factorial over r factorial times n minus r factorial. That's the formula to calculate the number of combinations. So that's the formula I used. Does that feel good? Yeah. So the 4 came from 6 for n minus 2 for r.
Yeah, but you didn't do, you didn't do minus anything, you just did 6 over 2.
I did 6 factorial over 2 factorial times 6 minus 2 factorial, because I assumed that 6 minus 2 we could do in our head and just say it was 4. Is that okay?
Yeah.
Okay. I just wanted, if you don't see it.
I got it.
Okay. Emerson, what's up?
How did you get the 2 over 3 instead of power below?
So this is us picking back up this problem that we started talking about, and you might not have been.
Okay.
So the situation there is at the top where we're tossing an unfair coin 6 times, where the probability of getting heads is 2/3. And we're trying to calculate the probability of getting exactly 2 heads.
Okay.
Right? Brooks, did you have a hand?
No, it's just how do you know, or there's more ways of arranging heads than just 2 ways, so why did you choose 2 first?
So it's not, R is not the number of ways, it's the number of heads in our outcome.
Okay.
So if you're arranging 6 things, right? You have 6 spots to put things. 2 of the spots have to be heads.
Okay.
And that calculation is counting the number of ways you can do that.
There's more ways to do it, it's just we need at least 2.
There's 6 factorial ways to arrange 6 things. But I have 2 different piles of things. I have heads and I have tails. I want the arrangements with exactly 2 heads in them.
Okay.
That's what I'm choosing out of that pile of all possible arrangements.
Okay.
Does that make sense?
Yeah, and then it knows you're talking about heads arrangement because of the layer equation.
Yeah, we're gonna formalize this and it'll be clear how I'm plugging stuff in. Yep. So we did this, right? All right. So here it comes, the big payoff here. So if x is binomially, that's a hard word to say, binomially distributed such that x is BNP, such that the probability of obtaining r successes out of n independent trials, when p is the probability of success for each trial, we're given by the equation p of x equals r is n choose r times p to the r times 1 minus p to the n minus r, where r is just some integer between 0 and n. So in our case, we did p of x equals 2, where n is 6 and p is 2/3, right? And then we just plug them into the formula. Now, depending on where you look, you might see this same formula written with a q instead of a 1 minus p. Remember we talked about that earlier? In some places we'll abbreviate the q, 1 minus p with a q. Good news is this formula will be given to you on any kind of assessment you take, whether in class or from the IB. You do not need to memorize this. Everybody still doing good? Okay. So let's look at an example here. Oh man, that's a mess. That's a later problem. It says x is binomially distributed with 6 trials and a probability of success equal to 0.2 for each attempt. Rewrite the above situation using symbols. So, because x is binomially distributed, we're told that in the problem, correct? So we start by writing x, squiggle, b, parenthesis, And then we need to put n comma p in there. What is the n in this situation? 6. And p is 0.2. So there's symbolically what the situation is, right? X is a binomial distribution, 6 comma 0.2. Everybody feel good so far? No big deal. We want to find the probability of getting exactly 4 successes. So what we want is the probability that X is equal to R when R is 4. So we can use our binomial distribution formula that we were just given. So if I plug in n for 6, r for 4, and p for 0.2, I can just kind of grind this through, put my combination formula in, expand my factorials out, do a little clever reducing. I get that, or 48 over 125, or just a shade over 1.5%. Heck of a lot better than drawing tree diagrams, right?
True.
Remember what we're replacing, what this formula is replacing, and how big of a hassle that is, especially if you had a lot of trials. You like tree diagrams? You'd go do one for flipping a coin 50 times.
Yeah, we'll do it.
Bring in the sheet of paper you squeeze that onto. You need like a side of a building and still use like 10-point font. All right. Let's say we want now the probability of getting at least 1 success. What does at least 1 mean?
It can be 1.
Greater than or equal to 1, right? So, how many outcomes are greater than or equal to 1 in this situation? That's 1, or 2, or 3, or 4, or 5, or 6. So I'd have to calculate 6 probabilities and add them together to do that. Or I could think about it as a complement, right? What is the complement of less than or equal to 1? I'm sorry, greater than or equal to 1, excuse me. The complement of greater than or equal to 1 is?
0.
Less than 1. And how many ways, or how many outcomes are less than 1? Just x equals 0, right? There's just one outcome. So 1 probability to compute. Which one would you rather do? Calculate 6 probabilities or 1 probability? 1. Does it matter which way you do? No, you'll get the same answer. It's just a question of how much work do you want to have to put into this. So, the complement of at least 1 would be less than 1, which is the same thing in a discrete sense as less than or equal to 0, which in this case is just equals 0. So I have that. And then I just do 1 minus that. And there's my answer, about 70, just a shade under 74%. Is everybody okay? Again, you could have done, yes. You could have done P of x equals 1 plus P of x equals 2 plus P of x equals 3, all the way out to P of x equals 6. That's okay. Not wrong to do that, but kind of like a lot of work. Okay. Now, to point out to you, the complement rule doesn't always help you with these inequality problems. So let's say we want to talk about the probability of getting 3 or fewer successes. That's a probability of x is less than or equal to 3. So that means I need the probability of x equals 0, 1, 2, and 3. If I try doing a complement here, that's going to be 1 minus the probability of x is greater than or equal to 4. And I still have 3 probabilities to calculate there, right? Probability x equals 4, 5, and 6. Here it's just like, this is not really much of a time saver by using a complement. You guys see that? So let's just do this one directly, just for the sake of argument. So finding p of x is less than or equal to 3. I'm left calculating these 4 probabilities. I just push each one of those through the probability formula, and then grind that through my calculator, and there we go. Is everybody okay there? All right, let's do another example. The probability that I get a bus to work on any morning is 0.4. What is the probability that in a working week of 5 days, I get a bus exactly twice? So the first step would be to
Right, x could be whatever it is.
well, you first, even before you can do that, you have to decide, is this a probability distribution? But yes, that's the first thing you want to do, is investigate that. So, is there a fixed number of trials? How many trials are there? 5, 1 for each day of the week, good. Is the probability known?
Yeah.
Yes. Is it fixed?
Yeah.
Yes. Do we have 2 outcomes?
Yeah.
Yeah, what are the 2 outcomes?
The bus works or
We make the bus or we don't, right? Okay. And then, are these independent? If I make the bus on Monday, does that affect me making the bus on Tuesday? Probably not, right? Doesn't seem like it would. So, we can say that x is b 5.4, and we're looking for then the probability that x is equal to 2. Everybody feel good as to how we sorted this out? This is typically the most difficult step for students, is reading the problem and sorting out what's going on. Yes, sir.
Why is x 2 because that's the number of outcomes?
It says, what is the probability that in a working week of 5 days, I will get a bus exactly twice?
Oh.
So it told me in the problem. That's where the 2 came from. Cool?
Maybe.
Okay. So, to do that, I just plug into my formula, grind that through in my calculator, and I'm done. What if I told you this formula is already built into your calculator?
What?
And you just have to know how to ask it.
Did you know that?
So, if you have your graphing calculator with you and you'd like to follow along, I invite you to take that out. If you'd like to borrow one from my desk to follow along on, because you're like, yo, Mr. Gulick, if I don't do it, I ain't going to remember it. There's a stack on my desk. You're welcome to help yourself. Here we go. Everybody got your calculator fired up and ready to rock and roll? Okay. You're going to power your calculator on. You're going to press the blue second button. And then you're going to find the bars button underneath the down arrow. Notice above the bars button it has the word DISTR. That's short for distributions. So go ahead and press that. And you should get a menu like this. So you'll see there are 2 different function options here that probably apply to what we're doing. There's binomial PDF and binomial CDF. Here's how you know which one you need. If you're doing a probability that x is equal to r, that is PDF. If you're doing a probability where x is less than or equal to r, that is a CDF. So P is equals, C is less than or equal. Everybody's okay? So if we want exactly x, or the catching the bus exactly twice, we want the PDF. So when you press enter on binomial PDF, this menu should come up. We fill in 5 trials. The probability of success is 0.4, and the number of successes is 2. And then we press paste. That'll put it on the home screen. You press enter again, and that's your answer. Does anybody have an older calculator whose operating system doesn't give you the menu? I think we might have hit the tipping point where nobody has old enough calculator that they don't have the menu anymore. Don't worry, I'm sure Texas Instruments will change their operating system here in the next couple of years and everyone will have chaos again. Anyway, let's do this new problem on our calculator. So it says, I will get a bus at most twice. So at most means less than or equal to. So because it's less than or equal to, we need to use the CDF. So when you do CDF 5.42, you should get 0.68 and change.
What does that mean again, like, with the question?
What does what mean with the question?
Like, why do we choose CDF again?
Because it was a less than or equal to.
Like, what was the lesson?
We wanted to calculate P of x less than or equal to 2.
Okay.
Because the question asks for at most twice. Right? So that means you could catch the bus 2 times, or 1 time, or 0 times. So alternatively, you could calculate this using 3 PDFs and calculate the probability x is equal to 0 plus the probability x is equal to 1 plus the probability of x is equal to 2, or you do a PDF for each one of those and add those together, you get the exact same value. That's fine, you can do that as well. Everybody good? All right. When administering a drug, it was known that 80% of people using it were cured. The testing program administered the drug to 2 groups of 10 patients. What is the probability that all 10 patients were cured from both groups? First step would be to
See if it's
see if it's binomial, right? So, we have a fixed number of trials.
yeah.
Yes, what is the number of trials? 10. Are there 2 true outcomes? Yes, what are they?
Cured or not cured.
Cured or not? Is the probability of success fixed?
Yeah.
Yes, right? What's the probability that somebody's cured? 80%. Is that changing for any reason? Doesn't seem like it, right? Nothing in there to indicate that. And are the outcome or the events independent? Is one person being cured independent of another person being cured? Me getting better isn't affecting you getting better at all, is it? No. Okay. Everybody convinced it's binomial? So if I want all people in the first group being cured, we want the probability that x is equal to 10. Everybody agree? How do I calculate that? I use my calculator, and what am I going to use? No! PDF equals means P. P equals. P equals. So we get that, but we have two groups, right? So that's just for the first group. How do I find the probability that both the first group and the second group are cured? Yeah, square it, right? Because the probability of x equals 10 and the probability of x equals 10, the two groups are identical, right? Same number of people in them, the same number or same percentage of success. They're ostensibly, statistically identical groups. This and this multiply them together, since they have the same probability, you're just like squaring it. So shade over 1%. Brooks.
What does 10 choose 10 mean? Like, you can arrange 10 different things 10 ways?
So it's choosing from a pool of 10 things, 10 successes.
So then why does it turn out to be 1?
Because the only way to get that is success, 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 success. There's only just one way that looks, right? Just everybody's cured. Because there's only 10 things, so if you're putting cures out, there's only one way to put out 10 cures to fill 10 places.
I just get confused with the end order.
Yeah. Yes,
I got
Colt.
0 when I did the PDF.
What did you type in?
The trials is 2.
Nope, trials is 10. That's why I gave you 0 probability, because you can't have 10 successes in 2 trials.
Then what's the x value? 10?
10.
So both 10?
Yes. Does that feel okay?
Yeah.
Again, because you're taking 10 people and hoping all 10 of them are cured. I don't care what expectation, expected value, right? Now you could do the formula from before, where we write out our whole probability distribution, then you multiply the value for x by the probability of x, and then you add all that stuff up. You could still do that. Yuck. Guess what? It's a nice formula here. Guess what it's going to be? N times P. Which shouldn't be a surprise, right? If I ask you, if I flip a coin, fair coin 4 times, how many times should heads come up? 2, right? You did 4, the number of trials, times a half, the probability of success, to get 2. It's exactly all we're doing here. That's nice, right? Now, nice and easy that was. Again, that's one that I think is going to be on the thingamajigger, the formulas. All right, let's look at this situation. A biased die is thrown 30 times. The number of 6s is seen. Boy, that's hard to read. The number of 6s seen is, it's a lot of S sounds all in a row, 8. The die is then thrown a further 12 times. Find the expected number of 6s for those 6 throws. So we're doing expected values. We want to do n times p. What is my value for n? 12. And my value for p?
8.
Well, that's an insane answer because the probability has to be between 0 and 1. So 8's like a crazy number. 8 out of 30, though, is the probability, because we have this sample where we saw, hey, 8 out of 30 times I get a 6, that's the best type of that's the type of probability I got. What should have we done before we started this though? Check if it's a binomial, right? So is this binomial?
Yes.
I mean, it's independent. There's two outcomes. It's either a 6 or not a 6. There's a fixed number of trials. I feel pretty good about this. Rolling a die is independent. That's a classic independent event. The only thing where you might be questionable about is the probability of success. But like, we have our best estimate we can do for that, whether that's exactly correct or not. It's empirical. It's fine. You know, it's like, anyway. So just do 12 times 8 out of 30 and we get 3.2. Similar to the expectation, we can calculate variance with just the formula, a simplified formula, as opposed to the nasty boy that we had to deal with in the previous section. So the formula for variance is just n times p times q. Remember, q is the probability of failure, so 1 minus p. And since variance is the standard deviation squared, what would our formula for standard deviation be then?
Square root of NPQ.
The square root of NPQ, which again, like, so very nice. Like, what a hassle variance and standard deviation was to calculate from a probability distribution using like the most general formula here in this special binomial case. Boy, that makes life so much easier. All right, let's look at an example. Find the expected number of workers in the sample that travel to work on public transport. Large company, 40% of the workers travel to work on public transport. A random sample of 15 workers is selected. Is it binomial?
Yeah.
Yeah, how do you know?
Independent.
Okay? Whether a worker rides public transportation or not doesn't affect the other one, so independent, yep.
Fixed.
Fixed number of trials is 15.
And it's not like one doesn't affect the other. It's
Yep, that's the independence piece. What else do we still need?
2 outcomes.
2 outcomes. What are the outcomes?
Worker traveling on public transportation or not.
Good, public transport or not. Everybody satisfied? Okay. The last thing is that the probability of success is fixed, but like, that kind of goes without saying. Okay, so we are binomial. So the number of trials was 15, and the probability of success is 0.4. So to calculate the expected value, what do?
Multiply 15.4.
Good, n times p. And I use w here as my random variable, probably for workers is probably what I was thinking. I know we use x so often as a random variable, I'm just trying to change it up. Everybody happy? So on average, we expect 6 workers to travel via public transport. Find the standard deviation. How do I do that?
the variance equation.
So I use the square root of the variance equation, which is np cubed. So what is my value for n? 15. What is my value for p? 0.4. And what is my value for q? 0.6. 1 minus 0.4. So there's my variance. And then to get the standard deviation, we just square root it. So what does that mean?
On average.
It means in a randomly selected group of 15 workers, on average, we have 6 workers travel by public transportation, and any such group on average would be plus or minus 1.9 workers away from that value. So on average, we'd expect to find the number of workers between 7.9 and 4.1. Everybody's okay? Let's look at some of our in-class examples. We won't do all of them probably, but we'll do several and leave the rest of them for you guys to look over. All right. There are 12 students in a class, and there are exactly 5 girls and 7 boys. You want to determine the probability of selecting 3 boys in a row with replacement if you were to select only 3 students at random. Who can explain to me how I know that X is binomial?
Fixed.
So fixed number of trials. How many trials are there? 3 is correct. Okay. What else? There's 4 things. So fixed number of trials. What's that, Anthony? Say it loud so we can all hear you.
Brown. Is it with replacement?
Yes, it says with replacement. Quinn,
There's only 2 outcomes.
2 outcomes. What are the 2 outcomes?
Girl or boy.
Girl or boy. Great. What else? We have 2 more now.
It doesn't that like independent because if you choose a girl, then like
It is independent, but that's not why.
and maybe that's why.
Oh, I think because
Anthony should know why because he asked about it already.
Oh, with replacement.
With replacement. Because we're replacing the names after we draw them. We do have independence. Good. And the last one is probability of success is fixed. And we know that's true because we have replacement still, right? Okay. So we can say that X is B what? No, I should do it down here. What's N? No.
oh, sorry, 3.
3. What's P? Quinn?
You?
7 out of 12. Great. Quinn, how'd you get 7 out of 12?
Because there's 7 boys out of the 12 students, and you're picking out of the 12 students.
Great. The probability of picking a boy is 7 out of 12 because there's 7 boys in the class of 12 people total. All right. Find the exact value of picking exactly 2 boys in the 3 trials. We want that. When I say exact value, what does that mean?
P.
Means no rounding. What does that mean? I want you to do it by hand so you can give me a fraction answer, unlike typing in your calculator. So this is me checking to see that you can plug things into the formula, right? So the formula is N, choose R, P to the R times Q to the N minus R. Oops. And now it's just like, I need the calculator to do some arithmetic for me, but like, I can hang on to my fraction, right? Unfortunately, I don't know 12 cubed off the top of my head. Sorry, guys. All right. Find P of x is less than 2 using your calculator. Who can give me that? Quick, it's a race. Get those buttons mashing. Mash those buttons. Who's gonna win it? The pressure's on.
Emerson.
Anthony?
Emerson?
What is, okay, 7. 12. You messed me up. I knew it was 12 too. I was listening to you. You know my head. I know you're not joking.
What is it?
Oh, wait.
Wait, oh.
0.8.
Emerson
Nope.
got 0.8.
Nope.
Oh my god, Emerson. Oh.
We're wrong.
That is wrong. I'll tell you what you did wrong.
Was it, we're using,
Oh, she did?
is it, I didn't see it.
You have to switch it up.
Shoot, I don't even know. Huh? But I'm confused.
Okay, how many boys are less than 2? How many boys can you draw that's less than 2? 1 or 0, which is less than or equal to 1. Now you're ready to do a CDF because you have a less than or equal to. You can't do a CDF on less than 1.
0.376.
There you go.
It's okay.
What you had before was the answer to this one, which is
0.802.
okay. Everybody feel okay here? Don't get tricked. Yeah, I know. There's a bunch of them in the example where I tried, where we really get you. You have to do some manipulations to get to the CDF part. All right. Next one. Go. Who can do A? It's a race.
Emerson?
It's nice because we're told it's binomial to start with, right?
0.12.
So, 0.273.
Yes.
Evan Asmar said 0.58.
Well,
That's not right.
I wouldn't cheat off Evan on this test. Find someone else to cheat off of. All right, next one. Who can do B?
Is it 0.022?
0.088.
Okay, that's what I want. 0.0879.
Oh, what did I do?
I'm not sure. But you see the danger on test. If you show no work, and all you do is leave me an answer, if it's wrong, there's not a lot of partial credit I can give you. So you gotta make sure that you're really right. Emerson, you have the last one already?
Oh, no. I have a question.
Yeah.
So if it's less than or equal to, we just put that number, and then when it's not less than, we put the number.
So think about it this way, right? We need to do some manipulation to this before we're ready to type it in as a CDF, right? So we have 8 trials. What are the outcomes that are greater than 6? 7 successes or 8 successes, right? So you could do this as this. That's fine. You could do it that way. Or greater than 6 means that your greater than or equal to 7, right? But that's not a CDF, because it's not less than or equal to. Or you can do 1 minus B is not greater than 6. What's not greater than 6 mean? Less than or equal to 6. And now this is one where you could CDF this.
So you would put 6.
We do 1 minus
Would it be 0.195?
0.195 is the answer.
So I did the last one, so you did 6.
So any way of kind of approaching that,
So that's not the answer. And then do 1. Because that's like,
is
the
okay.
answer is not 6.
This is probably the easiest button mashy route, but like this isn't much harder, right? So you got to really kind of think about what's going on, but whether you want to use a CDF or a bunch of PDFs, as long as the right answer is the right answer is the right answer. You know what I mean?
Last time you got it.
All right. Let H be Mr. Chun checks in homework. The probability that Mr. Chun will check in homework on a given day is 0.85. Assuming that each day is independent, write the following events in correct notation, then use your calculator to solve the indicated probability. Mr. Chun checks in homework 4 days in a row. So you should start here.
4, 0.5.
Great. And then we want to find the probability that X is it equal or less than? Or equal to or greater than? Or what are we writing here? Is it equal? Is it less than? Is it greater than? Is it less than or equal to? Is it greater than or equal to? What? Equals 4. Good. So you can just do a PDF to do this, right? Is everybody okay? Again, this part that we just did together is the hardest part, right? Typing in your calculator, not difficult. Understanding when you read it, like, okay, what's the probability distribution going on here, and what probability am I actually calculating in a language that I can get it into my calculator? That's the tricky part. Because you have to read and use your brain.
So would it be 4 for the trials and 2 for the
Yeah. Yeah.
Wait, what would be like an example of something that would be like less than or greater than?
Okay. Let's keep going. So for 3 consecutive days, Mr. Chun checks in homework exactly once. What's our binomial here?
3, 0.5.
Mm-hmm.
Nice.
And what probability are we calculating? What's that, Katie? Equals 1. What word or words in here told you that it was equals? Yeah. Exactly should mean equals. Okay? I'm going to skip the number computation piece because you're just typing in your calculator. I think the part that I'm more worried about these setups. Yeah? Okay. In a 5-day week, Mr. Chun checks in homework exactly 3 times. Yes. In a 5-day week, checks in homework at least 4 times. So hopefully everybody recognizes it's the same binomial here. At least 4. Greater than or equal to 4. Can I use my calculator to do this as it's currently written? No. Why not? The inequality must be either equals or less than or equal to are my only options. So you could write this as P of x equals 4 plus P of x equals 5. Those are the two outcomes that are greater than or equal to 4. Or you could do it 1 minus the probability that x is not greater than or equal to 4, which is 1 minus the probability that x is less than 4, which means 1 minus the probability that x is less than or equal to 3. So whether you want to do it either way, doesn't matter, you'll get the same result. Those are the two ways you go into your calculator, either using 2 PDFs or 1 CDF. The choice is yours.
So for this, if you did CDF, you did 3?
Yes. Does that make sense, Colby? Okay. In 2 consecutive 5-day weeks, Mr. Chun checks in homework at least 4 days each week.
Will you add them to it?
Nope. More Marin.
You would take your result from like the prior one from T and square it.
Yeah. So the probability of 4, at least 4 in week 1, and the probability of at least 4 in week 2. It's not or, right? It's and, because it's in both weeks. It has to happen both of them. It's and. So it's multiplication. It's not checks in at least 4 in week, the first week or the second week, in one of the 2 weeks. Right? Does that feel okay? So you can just square your answer from above. Yes. I think we're just about out of time here. There's a one last page where we're just calculating variances and standard deviations and expectations and stuff. It's just kind of using the formula. I don't think it's that big of a deal. As a heads up, we're looking at our chapter 12 quiz, probably Monday of next week. It's just going to cover 12.1 and 12.2. Tuesday of next week.
Wait, this is 12.2.
What's that?
This is 12.2.
This is 12.2. Yep, so just be covering 12.1 and 12.2.
Wait, it would be Wednesday.
Tuesday.
I don't know, what are the first class day next
We
week?
don't have school on Monday. In
Yeah,
our last class this
And that
week
would
is
be
on
a B day.
Thursday.
we don't have Friday mornings.
I know, is it not Tuesday? So our next class is Thursday.
Tuesday?
I think Tuesday and Thursday we have class next week, because we end on an A day this week.
Oh, yeah.
So we should start the first class day next week as a B day. I think we got it, right?
Yeah.
Okay. I'm not the best at the schedule, as you guys have all found out, but